so maybe I'll just leave it in this format for safety's sake. This is SM-based semantics for answer set programs containing conditional literals and arithmetic. And in particular, we're interested in defining semantics for answer set programs in a way that's convenient for formal verification purposes. And in particular, we want to be able to automate the verification of answer set programs. All right, so to begin with, we'll just consider basic answer set programming rules of the form head if series of body, b sub 1 through b sub n, where h is either an atom or it's empty, denoting it's a constraint. And each b sub I is singly, a doubly, or a non-negated atom. And alternatively, each b sub I could be a comparison between two terms, like x is less than 5. So this is a very traditional rule, but it has a very flat structure, which on the one hand is attractive from readability perspectives. On the other hand, it loses some of the expressivity that you might get with a first-order formula, where you can have arbitrary nesting of quantifiers and different connectives. So one kind of happy medium that at least the CLINGO answer set solver employs is allowing these body literals to be replaced with conditional literals. So a conditional literal is a structure of the form h such that L sub 1 through L sub m, where h is a basic literal, a comparison, or the symbol denoting falsity, and the list L sub 1 through L sub m is a list of basic literals and comparisons. And this improves upon the expressivity of our rules. So this is a traditional encoding of the graph coloring problem in this language that we're talking about today. This is an example that doesn't use conditional literals, but I'll show how we can refactor it. So the first rule is just a choice for assigning color to every vertex. The double negation is basically the choice rule syntax sugar stripped away. What I want to talk about is the third and fourth line, which is the constraint that every vertex must be colored. To achieve this, we have to introduce this auxiliary predicate colored, a verity 1, which is actually unnecessary, and it's problematic from a formal verification perspective because it extends our program signature. So if we want to talk about arguments of strong equivalence, for instance, this program is actually less than optimal because of this colored predicate. So what we can do is we can refactor this program and instead we can omit this colored a verity 1 definition and instead add this conditional literal that's the red expression. So we're saying for all vertices, it's impossible that it hasn't been assigned any color with this conditional literal. So to go forward, when we're talking about conditional literals, we have to talk about variables that are global to a rule versus variables that are local to a conditional literal. So in this example here, v is global because it occurs in the head, but not in the list of conditions within our conditional literals. It's also global because it occurs in the vertex v atom. All other variables, which in this case is only c, are considered local. So the intuition that we're going to formalize with these semantics is that conditional literals behave like nested implications within rule bodies, universally quantified over the local variables. And again, the motivation for this is automating the process of program verification and extending the class of programs for which we can apply this automated verification. So Anthem's a tool that I've been developing in collaboration with a number of other people at Potsdam and also Vladimir Lifshitz from UT Austin. It's a tool written in Rust, and it uses the theorem prover vampire as a backend. So the main types of claims that we can automate with the Anthem tool are checking the equivalence of two ASP programs, in particular those written in the input language of CLINGO. And the other thing we can check is that an ASP actually adheres to a first order, an ASP program adheres to a first order specification. What this work is trying to do is taking steps towards extending Anthem with conditional literals. So to do that, we first have to define the semantics of an extended language in essentially first order logic. That's the eventual goal. All right. So as a background, I should talk about the logic of here and there, or HT, because of its close relationship with ASP. And I won't review the exact semantics of it, but I will say that it's a non-classical logic and it's intermediate between intuitionistic and classical first-order logic. So we consider in this work a mini-sorted variant of HT, where we have two universes, the first that consists of all program terms, and the second is a subsort of that universe. It contains an integer-like type that we call numerals. So equilibrium logic is an entailment relation for HT, and the intuition is that it introduces a stability condition on HT models. And there's been a lot of work showing the relationship with equilibrium models and the stable model semantics in terms of redux and so forth. So I'll talk about strong equivalence, which is denoted with this equality S symbol a lot as well. Formulas are strongly equivalent if they're HT equivalent, and programs are strongly equivalent, or ASP programs are strongly equivalent, if they have the same answer sets when paired with any other ASP program. And the nice relationship between ASP and HT allows us to check strong equivalence by checking HT equivalence. All right, so the input language of CLINGO is called abstract Gringo, or HD, and technically the semantics are defined in terms of a translation tau into infinitary propositional formulas. So as a very simple example, if we have the rule P of x if Q of x plus 1, then tau applied to pi is the theory that consists of tau applied to all the ground instances of the rules. So that's where we replace x with all the possible symbolic constants, for instance, and all the possible numeral. So one important restriction of tau is that it replaces these conditions on the legal values of terms. So a term like 1 plus 1 has just one value. It has the numeral 2, whereas 1 plus a doesn't have any values, for instance. So the translation tau basically takes a disjunction across atoms with respect to all the possible legal terms. So in the case of symbolic constants like a, there are no terms, so it's an empty disjunction. Whereas in the case of numerals, we have exactly one value. So we can simplify the tau transformation into basically this infinite series of conjunctions across numerals. So Q of 2 implies P of 1, Q of 3 implies P of 2, and so forth. So because CLINGO promises to compute the equilibrium models of tau pi, we would actually like to lift this characterization to a first order setting so that we can avoid this infinitary context, which the main motivation for that is we want to use automated theorem provers for formal verification purposes. There are two steps we need for this. The first is that we need to replace tau with some kind of translation to first order formulas. And traditionally, these translations have been called tau star. The second step is we need to reduce the task of HT reasoning to classical reasoning. All right, so Mini Gringo is a fragment of the abstract Gringo language, and it does support arithmetic, which is one of the complicated features of the language due to this values of terms condition. The idea is that the semantics are captured via translation tau star into the syntax of first order formulas. But again, these formulas are interpreted under the HT semantics. We'll need additional transformations if we want to interpret them classically. So, as a quick example, tau star of pi applied to this same rule is going to be a fairly complicated formula, but it's strongly equivalent to a much simpler formula, which reads, for all x, if there exists an integer I such that I is equal to x, and q holds for I plus 1, then we conclude p of x. So when I use I and j and so forth, these refer to integer variables. Otherwise, they refer to variables that range over all program terms. So our goal is to extend this mini Gringo language with its support for integer arithmetic to programs that contain conditional literals. So one thing we've been interested in addition to conditional literals, is an extension to programs with aggregates. So integer arithmetic, conditional literals, aggregates, we've studied them all kind of in separation from each other. And this work is our first step into trying to bridge them all. So that puts us at the red dot, the intersection between arithmetic and conditional literals. The eventual goal for my dissertation, at least, is to bring both conditional literals and aggregates into this translation for mini-gringo. All right, so to accomplish this, here's kind of an overview of the approach. We've got a variety of different logical formalisms and different ways of connecting the semantics of ASP programs within them. So if we have a logic program P, we know that we can transform it via the tau transformation into infinitary propositional formulas interpreted under the HT semantics. And this is basically what captures the behavior of CLINGO. On the other hand, we want to design translations into the world of many-sorted HT formulas via variants of tau star, because what we can then do is apply transformations on top of that tau star transformation, such as the SM operator, which is what I'll talk about today. Basically, that takes us into the world of classical second-order formulas, and there are known relationships between the results of applying SM to many-sorted HT formulas and the corresponding infinitary propositional formulas that you can obtain via a process known as grounding. All right, so some important features of the tau star transformation. I won't talk about the entire transformation, but basically, if we have a formula val t of v, it denotes that v is a value of term t. So for example, if we have this compound term val of x plus 1 interval 5, that's CLINGO notation, of v, we can view this as the first order formula. There exists integers I and j such that v equals I plus j and x equals I, and j is one of the values in the interval from 1 to 5. And I didn't expand that formula. So if we want to translate a basic literal within a rule body, we have to take into account the global variables. So basically, we have a body translation, tau b of z, which translates atomic formulas in a rule body into first-order formulas. So for example, the literal not p of the term 1 interval 5 is there exists some v such that v is a value in 1 to 5, and not p of v holds. Here, the negation symbol is the HT negation symbol, which corresponds to ASP's default negation, or negation as failure. Not classical negation. That's the important point. The translation that we add to this existing tau star transformation is treatment for conditional literals. So if we have a conditional literal with local variables bold x, we would translate it into the universal closure across these local variables x, where the translation of the body literals conjoined implies the translation of the head of the conditional literal. So that was the main idea, that conditional literals behave like nested implications. The real challenge then was establishing that this is actually what CLINGO computes. So as a running example, we would translate our conditional literal from the graph coloring program as follows. This is more complicated than it needs to be because there isn't any integer arithmetic in this rule. So this conditional literal constraint is actually, its translation is strongly equivalent to a simpler rule which states for all vertices v, if v is a vertex, and for all c, color c implies that v has not been assigned to c, then we have falsity. So again, that's just an intuition behind the translation of a constraint rule in ASP. So the SM operator is convenient because it allows us to specify intentional predicates, and these are basically the predicates in which we minimize our belief. This is, in a lot of ways, a more convenient representation than the equilibrium models representation. So if we have a mini-sorted first-order formula and we have a list of predicate constants, SMP of f denotes this second-order formula. F conjoined with there does not exist u U is a tuple of predicates whose extent is less than P, and F star of U holds. So here, F star of U, you can think of it as a transformation that's embedding the behavior of HT satisfaction within a classical second order formula. And the condition that it's not the case that U is strictly less than P behaves analogously to the stability condition of equilibrium models in that we minimize our belief in intentional predicates. So in ASP, typically one of the rules is we don't believe anything we don't have to believe. On the other hand, there are certain predicates where we don't minimize belief. So for instance, the comparisons like equality, we don't minimize our belief in that analogously to other ASP predicates. All right, so for many sorted first order sentences from a signature, we call the models of S and P of F the P-stable models of F. We consider only standard interpretations that give a traditional treatment to arithmetic operators, plus, minus, times, and absolute value. We also assume other conditions like a Herbrand interpretation of symbolic constants. So finally, this brings us to our proposed semantics, which states if pi is a program and P is a list of all predicate symbols other than the comparison symbols, then the atoms satisfied by a standard interpretation are answer sets of the original program when this interpretation is a P-stable model of tau star applied to pi. All right, so to prove this, we had to prove that this definition was equivalent to the definition of CLINGO's behavior, which are called CLINGO answer sets. Basically, they're equilibrium models of tau pi. To establish this, we use the strong equivalence of infinitary propositional formulas. So the main piece of this work was proposition 2, which establishes that for a closed conditional literal, which means that all global variables have been replaced by program terms, then for a standard interpretation and the standard partition P, the grounding of tau B of z applied to this conditional literal is strongly equivalent to tau applied to this conditional literal. And here the standard partition just means that we treat all predicates except for the comparison symbols as intentional. All right, so our proposition 4 extends this to show that basically tau star, after the grounding operation has been applied, is going to be strongly equivalent to tau of pi. From this we can conclude theorem 1, which establishes the correspondence between the infinitary equilibrium models of this syntactic object grounding applied to tau star of pi and the infinitary equilibrium models of tau of pi. And our main theorem basically establishes that, yes, our SM-based characterization of answer set semantics captures the behavior of CLINGO. All right, so I do want to talk, because this has all been like purely theoretical, I want to talk about what I've been working on since this paper was sent here, which is actually implementing this within the Anthem tool, because that's the eventual goal for this. So here are some very simple examples that we've verified. For instance, this example here replaces a choice rule in the first line with a conditional literal in the second line. It's been verified by hand in the past by the developers of the tau transformation, but now we can actually automate the verification of the equivalence, the strong equivalence of these rules by invoking Anthem with the command here. On the other hand, if we were interested in checking that our alternative versions of the graph coloring program are externally equivalent, which is to say that they have the same output for a certain predicate when paired with the same set of input facts, we can verify this automatically by invoking Anthem with the external equivalence verification pipeline. Again, these aren't strongly equivalent programs, but they are externally equivalent, which is a different notion we've been developing. All right, so to wrap up, this paper extends the mini CLINGO language with conditional literals. And then we define the semantics of the language by extending the tau star transformation and applying a mini sorted variant of the SM operator to it. And we've proven that the proposed semantics actually capture the behavior of CLINGO via strong equivalence. One of the reasons we pursued this is because it's a roadmap for this more challenging next step, which is trying to integrate aggregates into this language, which will require some additional work. And that's the main focus of future work, is extending this tool with conditional literals and with aggregates. All right, thank you.
I can ask some questions. So you motivated this work for augmenting ASP with kind of verification capabilities, right? So towards formal methods, and strong equivalence is something that we want to be able to prove automatically by using these kind of tools. So do you have in mind some other forms of verification that may be useful? Not necessarily about strong equivalence, but maybe some other properties of, for instance, ASP programs.
So maybe I'll go back to, because I kind of glossed over this external equivalence characterization. There's actually a couple of different things we can test using this idea. On the one hand, we can check that two ASP programs have this special type of uniform relativized equivalence. On the other hand, we can check that a specification partially specifies the behavior of an ASP program. So if we write a specification in first order logic, we can check two things. We can check that the ASP program has the properties in this specification, or we could check that the specification completely defines the behavior. So there's an equivalence, an external equivalence between these two. So a special case of this would be checking answer set equivalence between two programs. That would be a special case of external equivalence. Beyond that, there's one thing I'm interested in is extending strong equivalence to programs with input and output. A lot of times we'll use placeholders in ASP programs, and it would be interesting to have some notion that two programs are strongly equivalent under certain assumptions governing the assignment of the placeholders, for instance, like that they're interpreted as integers, for instance.
Yeah, that's one more question. Yeah. So you said that you want to extend this work to aggregates.
Mm-hmm.
Along that direction, do you think that first order will be sufficient, or will you have to move to a higher order?
Yeah, that's a really good question, and I think it's something we're not quite clear on. So we've been working with aggregates, trying to go back. Yeah, here we go. So we've actually got a paper at AAAI, this upcoming AAAI, where we define the semantics of aggregates as intentional functions interpreted under the HT semantics. So we have a pretty good understanding of how they should behave within the world of equilibrium logic, for instance. And there are reductions to first order logic. In fact, I think I had it. Yeah, this gamma transformation, gamma applied to tau star of pi, is one way that we can transform these many-sorted HT formulas with intentional function constants into formulas interpreted under the first order semantics. The problem is we need to have a bunch of additional axiomatizations governing our standard interpretation for aggregates. So for instance, we need to express that we have a sort representing sets of tuples, for instance. So we need a tuple sort, we need a set sort. With integer arithmetic, we've been able to use Vampire's native partial axiomatization of like integer arithmetic to overcome this issue. but they don't have something like that built in for sets and sets of tuples. So that's an ongoing question of, you know, there are lots of partial axiomatizations of set theory within the thousands of problems for theorem provers library, which is where we're drawing some inspiration for this, but it's definitely a challenging question.
So in the paper, when you talk about giving interpretation to like non-ground interpretation answer set programs, that's referring to the tau star operator. Is that a correct understanding of how those pieces fit together?
ASP program into something that's syntactically first order logic but should be interpreted under HT. And then we can apply additional transformations like Clark's completion or the gamma transformation to obtain formulas that can be interpreted under classical first order logic.
So is it potentially meaningful to take that interpretation and sort of run it like, you know, as a feed that to a solver and thus get kind of an interpretation for non-ground answer set programming? Is that like this tau star operator seems really interesting in the way that you're like pushing the semantics of answer set programming?
So you could definitely use like Z3, I think, would be an example of something where you could give it the formulas obtained via completion and tau star, and it could compute basically the stable models of the original program, which I think is how a SAT works. So there has been some research into doing this.
This talk and the perspective into a lot of different pieces that you have put together here.